So welcome, and I'll hand over to Nick to introduce our first seminar speaker.
All right, so thanks to everyone who's made it out or made it in or whatever. So I'm doing this from my brother-in-law's place in upstate New York, actually. So I guess that's the nice thing with these remote talks, is that we have no excuse to not participate because you can do it from anywhere. So anyhow, so it's my pleasure to introduce Elodie Ebrard, who was willing to give the very first inaugural TEPS talk. So Elodie did her PhD in Toulouse at IRAP, the Institut de Recherche en Astrophysique et Planetologie, with J.F. Donati. She got her PhD in 2015. She's an expert on HARPS and Espadon and exoplanet observations and the host stars of exoplanets, and has been a postdoc at York with Ray J since then. So take it away, Elodie. Oh, and I guess I have one last thing to say, which is, please mute yourself when you're not talking. But I think when John and I talked about this earlier, we would like people to feel free to ask questions during the talk. And the mic at York is a little bit weak. So if people at York ask questions, Elodie, please repeat their questions so that those of us online can hear what they said. Before giving your answer. And then those of us who are Skyping in online, we just have to remember to mute ourselves when we're not asking a question. And that's it. All right, good luck.
Okay, thank you. Okay, so let's go with this presentation. Exoplanets hidden by stellar activity. So it's projects I do in my PhD and that I continue to do here. And with all of this. So to start, let's just introduce the kind of exoplanets discovered so far. So on the y-axis, you have the mass of the host planets, and on the x-axis, you have the distance between the planets and the host star in astronomical units. So for example, if you put the Jupiter and the Earth, all of the solar system is on this horizontal line here. And you can see each symbol is an exoplanet, and the color is directly representing the mass of the planet. So if you have a yellow, orange, red symbol, it's a giant planet. If it's more blue or green, it's a rocky planet. So what you can see first is that most of the exoplanets discovered so far has been around solar-type star. This is more an observational.
Yeah, that's okay.
It's more an observational bias because all the instruments so far, most of them are more sensitive in the visible domain, and these stars emit massively in the visible. And then we can look at the color of the point. Most of the blue or green here, most of the blue or green exoplanets are very close to the host star, and whereas you can have the very massive far from the host star. This is also an observational bias because if the planet is very big, it's easy to detect the planet even if the planet is far from the star, but if the planet is very small, or you have a mass-like planet, the signal is very small, so it's easier to detect this planet close to the star. And finally, very few very few exoplanets, around NROS, because NROS massively emits in the infrared, so we need infrared high-resolution spectrum to detect them. And if you look into the habitable zone, so if you want to detect a host-like planet in the habitable zone, habitable just means liquid water, maybe stable at the surface of the planet. You see that if you want to do this, it will be very easier to detect this planet all around NROS. So we need to build and to use infrared instruments to detect this kind of planets. Okay. So a detection, it's more than just say, okay, we have a planet here. We want to physically characterize the planet, so it means we want to have the radius of the planet, the mass of the planet, characterize the atmosphere of this planet to be able to characterize its habitability. And then we need to detect lots of exoplanets to improve the statistic and to improve the way to improve the planet formation scenario. And finally, we need to characterize the environment that surrounds the planet to better constrain the habitability, because just water at the surface of the star is not enough to make a planet. And to do so, we need to minimize all the observational bias, and it means use different techniques, different wavelengths, and very high resolution instruments to improve our ability at detecting all these different parameters. But there is always a but. All these techniques are indirect, so it means that we are focusing on the star and not only planets. So we are very sensitive to all the variability of the star when we want to detect small planets or when we want to detect exoplanets in general. So this is the example of the radial velocity method. You detect the small shift of the whole spectrum during the revolution of the planets around the star to detect the planets. But you are looking into the spectrum of the star. So you are highly sensitive to the stellar variability. And you have different kind of stellar variability. You have pulsation and granulation, different kind of activity with different scale, spatial scales, and time scale. So pulsation and granulation, they are very with a very high period, so second or minutes, and on small scales. Then you have spots, so dark region or bright region, and the periodicity of the signal induced by this kind of features is totally commensurate to the rotational period of the star, so a few days, few weeks, few months, depending on the star. And then if you have a data set over several years, you might be sensitive to the stellar magnetic cycle, and you can also want to correct this. So from now, I will be focusing only on radial velocity. So to measure, to detect a planet using radial velocity method, you need to have a high resolution spectrum. In the spectrum, you expected a line for each, for example, absorption line. But due to the rotation of the star, you have a large line, so a profile, due to the Doppler effect. And if you have a planet, this profile will be shifted because of the radial motion of the star. And finally, because of the activity, which is mainly magnetically driven, you will have a distortion of the spectral line. So you have something which is enlarged and distorted by the activity. So in terms of radial velocity, granulation and pulsation, you will have an amplitude about centimeter per second, meter per second. Spots and plages depend on the stellar type, but you can have some few meter per second to hundreds meter per second. And finally, for the stellar cycle, you can have something with an amplitude about some centimeter per second to meter per second, depending on the stellar type. But if you have a small data set, the most important effect will be bright and dark area, because the periodicity is very similar to the orbital period of the planet you want to detect, few days, few weeks, few months. And the amplitude is also very similar to the signal of the planet you want to detect, few meters per second, or few hundred meters per second. So we really need to deal with this effect. We need to understand it to model and filter out the effect on the radial velocity curve. So now how does it work? You have a star which is rotating. So the part of the star which is approaching from you is blue shifted, whereas the part of the star which is receding from you is red shifted. Now if you put spot on this star, If the spots cross the part of the star of the spectrum which is blue shifted, we will have a net redshift of the spectrum. So it's what we see on the plot number 1. When the spot here is on the neutral part, on the center part, cross the line of sight, you have no red or blue shift, but just a profile which is less deep. And then if the spot is on the red shifted part of the spectrum, you will have a net blue shift of the spectrum. So you have an apparent radial velocity, which is due only to spots that cross the line of sight during the rotation cycle of the star. Then you have this effect. So if you look closer to the surface of the star, this is just a cell, a network of cells with bright, the center is bright, and it's surrounded by dark areas. The center is bright, so you have an outgoing flow. As it is outgoing, it is blue shifted. And on the dark area, it's sinking flow, so it's receiving from you, so it's red shifted. The net result is a blue shift. But if you have an activity region at the surface of the star, you stop this blue shift, you suppress this effect, and then you have annihilation of this effect, and then a blue shift of the spectrum, which is modulated by the rotation of the star, and then again, radial velocity effect. So finally, what do you get? This is a typical sampling of the star. So you get intensity profile. The number on the left, on the right, sorry, the observational phase. And if there is no planets, no jitter, nothing, you just have the same profile again and again. If you have a jitter, so you have plage and spots at the surface of the star, you have a distortion of the spectrum line as the star rotates. Now you have just the planets, no jitter, you just have the same profile that's shifted periodically according to the orbital period of the star. And what you have in general is a mix between the two, so you have a shift distorted profile. So you really need to disentangle the two effects to see the planet behind, because like this, you mainly see the jitter. And we can, for example, when the profile is very flat like this, it's a spot that crosses the line of sight. Whereas when you have a very sharp profile like here, it's bright spots that cross the line of sight. And in terms of radial velocity, if there is nothing, of course, you have just 0. If you have just a jitter, you have a periodic curve with a periodicity commensurate to the rotational period of the star. Just the planet, so you have a radial velocity with the orbital period at periodicity. And finally, you have, in general, a mix of the two. So to disentangle the two effects, we first have to diagnose which effect is the most important, the activity of the planet. And then, if you want to see the planet behind, we need to model and filter out this effect.
Melody, just a quick question while you're on this slide here. Is the magnitude of the jitter, is that typical what's shown there, or is it much bigger than usual?
This is a typical example of very young star. So for very young star, the amplitude of the jitter is about kilometers per second. And you want to detect, for example, very hot Jupiter. So you have planetary signal of about a few hundred meters. So this is not for habitable zone. This is just for hot Jupiter around very young star.
Thanks.
Okay, so to disentangle the two effects, you have a choice. Either you're lucky and the orbital period of the planets and the rotational period of the star are different enough not to be sensitive to this effect, and you can use clever selection of targets and observational strategy to deal with the two effects. Or they're totally commensurate, and then you have to diagnose, model, and filter out this effect. And I'm going to speak about a technique we developed, which is based on spectropolarimetric observation. So because we want to use imaging, so we want to map the surface of the star, find which distribution of spots we have, and then model the activity RV jitter due to this spot distribution to filter out the signal. And to do this is particularly effective if you have efficiency. If you have an activity signal which is dominated by the effect of spots and plage, and this is the case in two cases. For very young star, the spots and plage effect is dominating your signal. And for M dwarfs, whereas for sunlight star, this is the annihilation of the convective bit shift, which is the most dominant in the RV jitter. And whatever the case you want to study, the rotational period of the star is a key parameter, because if you don't know the rotation period of the star, it's more complicated to determine two effects. So that's why spectropolarimetry will be very useful. But before, how to diagnose the activity and how to diagnose the origin of your RV measurements. So first, you can measure the distortion of the line. If the line is distorted, this is mainly due to spots or activity rather than a planet. Then you can use some activity proxies like emission of calcium, H-alpha, helium, sodium, depending on the spectral type. Some of them are more useful than the other. But you can use this line if there is like a periodic variation of this line. You can also guess that the RV measurement you have is mainly due to activity. You can use also different spectral domain, because the planet will shift all the electromagnetic domain, whereas the activity will be wavelength sensitive, so a big effect in visible, a smaller effect in infrared or in the infrared. The photometry also, to see if there is some variability of the luminosity of the star. And the spectropolarimetry, because most of the activity is magnetic electrolyte. So maybe if you have the magnetic field of the star, you can also improve the characterization of the activity of the star. So spectropolarimetry. So with a spectropolarimetric measurement, you have two information: the circular polarization and the uncolorized spectra, which means the intensity profile, the standard intensity profile. So to get the polarization, which is a very tiny signal, we need to use some least square decomposition technique. So it means we average the measurements of thousands line just to increase this polarization signal, and we get this kind of spectrum. The red one is the Stokes V parameter, so the circular polarization. And the blue one is an intensity profile you can have for the standard star. With Stokes I, we measure the radial velocity. So because of the rotation of the star, you have this Doppler broadening. Because of the planet, if there is a planet, you have a shift of the spectrum. And because of spots and plage, you have a distortion. For example, like this. You add the star rotates, you have a distortion of the profile that you use this fake RV signal you want to filter out. And so the idea of the imaging technique is you have brightness feature at the surface of the star. Because of the Doppler effect, you will have some Stokes I distortion. And this is your data, so you want to do the reverse way. And from the distortion, you can get this map of the distribution of the spots at the surface of the star. With Stokes I, you will also be sensitive to the Zeeman splitting because of this. All spots and plage are magnetic. So because of this magnetic field, you will have a splitting of the line. And the splitting is proportional to the wavelength and to the magnetic field. So if you are in the infrared particularly, you will be very sensitive to this effect. And for example, this spot is not a dark or bright spot, it's just a magnetic spot. So the same temperature as the photosphere, but there is a magnetic field inside. And you see that this magnetic field distorts the line as well. And you can have here some a radial velocity signal with an amplitude about meter per second, depending on the strength of the magnetic field. So in the infrared, we will have to take into account these effects too. And because of the Zeeman effect, you can also measure the polarization. So if your line of sight is in the same alignment as the magnetic field, you will be able to measure, for example, the circular polarization here. And it's what you get with the Fox-V measurements. You will be able to determine very precisely the rotation period of the star. And because a magnetic field at the surface of the star, and because of the Zeeman effect, you have a polarization in spectral line. And with the, for example, if you have a radial field, so the first movie here, the magnetic field points toward you, and you have a Fox-V signature, which has always the same shape, but the intensity varies. Whereas if you have an azimuthal field, which is pointing toward you and then toward the board, you see that the shape and the intensity of the profile varies. So usually you have a mix between radial, azimuthal, and meridian field. But we can reconstruct like this a map of the magnetic field at the surface of the star, thanks to the demand of volume. So finally, if you have a spectropolarimetric data set of a star with exoplanets, you can map the spot distribution, the magnetic field. So this is important to have both the rotation period of the star to filter out the activity jitter, and also to have an idea of the magnetic environment that surrounds the planet. And it's important if you're interested in the habitability of the planet. So I'm going to present you an example, which is very simple, on a pre-main sequence star, so a Tittori star, reclined Tittori star, so no more accretion disks around the star. So, and we will apply this method in 2 steps. First, we do the Doppler imaging to map the surface of the star. From the map, we infer the radial velocity jitter. We filter out this from the measurements, and we see if there is any planets behind this activity jitter. And we will do this on Matisse observation. So Matisse is a large program carried with Espadon in Mauna Kea, CFHT. So for magnetic topology of young stars and survival closely massive exoplanets. So the observation of B832, we have about 40 observations over, say, 3 months of this reclined Tittori star, which is 1 solar massive, 2 million years old, so very young star, and with a rotation period of 2.7 days. And this is what we get. This is the spectrum we get. So in black, you have the observation, and it's very hard to see, but you have in blue and in red the model you get from the Zeeman Doppler imaging. So each spectrum is an observation of phase, and from this modeling, we can have this map of the star. So this is a flat polar projection of the star. So the center here, this is the pole. This is the equator, and this is minus 30 degrees latitude. So you can see when it's brown like this, it's a dark spot, and when it's blue like this, it's a bright spot. So we get this map here. The resolution is quite good because the distance is more than 20 kilometers per second. And we find that about 50% of the star is covered by spots or bright spots or dark spots. So it means a very big rotation, a very big radial velocity effect. So this is for the first panel. You have the raw measurements of the radial velocity. So each point is a radial velocity measurement. The color is for each rotational cycle. So this is rotational cycle 1, with, in blue the number 2, in pink number 3, etc. And in very light blue, you have the modelization of the radial velocity we deduced from the previous map I showed you. So we took this map, we took all the spectra, the model spectra from this map, and we compute the radial velocity. And this is what we get here. We remove this contribution, and this is what we get on the second panel here. So this is the other measurement without the activity data, and you can see a periodic variation of the signal. And the variation of the signal is certainly due to a hot Jupiter, which is orbiting this planet. And if we remove the contribution of the planet, we have the third panel. So in the third panel, we removed the activity and the planet. So we just have some residual. And the dispersion of this residual is about 20-30 meters per second, which is the precision of the instrument. So we can do better with this measurement. So to this curve here, corresponds to a hot Jupiter with a mass of 0.77 Jupiter mass and orbiting at less than 0.6 AU from the hot star. So it's a very hot Jupiter, and the orbital period is almost 5 days. This is the periodogram of the radial velocity measurement. So on the first one, it's just the raw measurement. So you have this peak here, which is the main one is due to the rotation of the star and the different harmonics. And you can see there is nothing at the orbital period of the star, but once you remove the activity signal, you clearly see that this peak here appears, which is the orbital period of your hot Jupiter. And once you filter everything, there is no more very big peak in your data. So you filter all the signal of your data. To be sure to efficiently filter the signal, we decided to operate differently. This time we filter simultaneously the planets and the Jupiter, because in the previous technique, we modeled the activity, and then we looked into the residual if there is a planet or not. This time, we will filter both planets and the shift and the activity. And this is what we get. The most likely planet is the same as the one previously. So, hot Jupiter with 0.7, 0.8 Jupiter mass and an orbital period of about 5 days. And finally, we apply a totally different technique. No more imaging, no more Zeeman imaging, just Gaussian process. So we analyze the correlated noise in our data. And we try to model simultaneously a Keplerian for the planet and a quasi pseudo-periodic signal for the activity Jupiter. And it appears exactly the same planet, so a hot Jupiter of 0.7 Jupiter mass with 5 days as the orbital period. So we have here around this very young star, 2 million years old, we have a baby planet orbiting this star with a Jupiter-like planet, and this has some consequences for the planet formation scenario. It means that the migration of these planets can occur very early in the lifetime of the star. after 2 million years, you already have this very hot Jupiter. So around main sequence stars, we found about 1% of hot Jupiter. On the Matisse sample, so far we analyzed between 10 and 15 stars, and we have only already one measurement. And in the paper of Lee Zhu, which is a PhD student working on this Matisse data, we have another one, TEPS, around TEPS, so, which is another hot Jupiter around a young star. This star is less young, but still it's about 5 or 4 million years. So finally, migration of hot Jupiter might occur very early, and this is in favor of a scenario where the migration is due to disk-planet interaction. We can apply this same kind of technique for very slow rotating stars, so M-dwarfs. So M-dwarfs are interesting if you want to detect Earth-like planets in the habitable zone. But the problem of M-dwarfs is that the Vistana is very small. The activity jitter is about meter per second rather than kilometer per second for the star. And the signal of the planet is about meter per second too. So everything is smaller. So you need to be much more sensitive. And the effect is mainly, the activity jitter is mainly due to spots and bright spots. But as the rotation is slow, you don't know the profile of the star very well, because usually the profile of the star is totally dominated by the Riemann broadening. But if you have a Vistana of 1 or 2 kilometers per second, it is not the case anymore. You're more sensitive to the intrinsic profile of the star, and we don't know this profile. So we need to have a more, the technique is actually more tricky. We need to compute the residual profile to control the brightness map. We can do this anyway for the most active dwarfs. And for example, this is what we get. This is M2 dwarf. And you can clearly see that you have a component which is due to the rotation, which is due to spots at the surface of the star, but also you can see that the spot lifetime is about 2 or 3 rotations of the star. Because between this map here and this map here, you have a difference of 2 rotational cycles, and you see that this spot slowly disappears, and this one appears, and 2 rotational cycles later, it is more and more present, and this one appears. So you can see that spots at the surface of very active star, even if they're slow rotator, can have a short lifetime. So we have to deal with this also if we want to discover, if we want to detect Earth-like planetary dwarfs. And we are looking if you can find any correlation between the topology of the magnetic field and the spot distribution at the surface of the star. So far, we have a very small sample of only 10 stars. So the sample is small because the only instrument which is able to do this kind of measurement, because we need simultaneously the magnetic field and a high precision radial velocity. It's APSPOL. And for the 10 stars we found that if the magnetic field is significantly colloidal, the spots are close to the magnetic pole, and if it's more toroidal, spots are more close to the magnetic equator. So this result will be very useful for SPIRO, which is a next generation spectral polarimeter. So SPIRO is for spectral polarimeter infrared. So it will be on the sky late 2017, early 2018. On the CFHT, the radial velocity precision will be about 1 meter per second, the resolution 75,000, and the spectral movement is about 1 to 2.3 micron. The main goal, the two main goals of SPIRO would be to target free sequence star, to understand the magnetic field dynamo, to understand the planet formation if we can detect young planets like hot Jupiter and Venus. And the second one, of course, will be to detect Earth-like planets around lunar star, and of course, Earth-like planets into the horizon to be more exciting. And to do this, they want to target about 300 planets, and we can have some answer about the magnetic field dynamo, about the habitability, sorry. And to characterize the atmosphere, we will work in synergy with GWST and TEPS, for example, to characterize the atmosphere of the planets, solar atmosphere. And it's under construction right now. So just to give you some about this instrument, everything is arriving in Toulouse because the instrument is built in Toulouse, but the different part comes from mainly Canada and France. So for example, this is the spectrometer here. So this is, for example, the collimator, the science camera is here, the prism are here. This is the cryostat here. So it has been built in Victoria, Canada. So you can have the size, for example, the engineer in France. So this is the cryostat because we are working in the infrared, so we need to cool everything very precisely. This is the gas-gram module just behind, which will be just behind the telescope, and where the polarimeter module will be. And okay, this is, for example, the collimator here, the science camera built in Montreal, and this is the prism. In zinc selenium, because we are working in infrared, it's a little bit different than the technology used for the visible spectral. Thank you. Hope it's
Can I try asking a question remotely?
Yeah.
Awesome. So I have two questions. One of them, I'll start with the easier one, which is the one that's more pessimistic. So is the deal that granulation, the spectral polarimetry does not help you with granulation because granulation doesn't have anything to do with magnetic fields? Is that correct?
I'm sorry, I can't hear your question.
Oh, sorry. So I'm asking about granulation. So I guess for sun-like stars, the limiting factor for doing high precision radial velocity, I thought, is granulation. Like if you're trying to do, 10 centimeter per second, the kind of stuff that Deborah Fisher is looking for. And at first, I was really optimistic that the spectral polarimetry might help with removing the effects of granulation. But then I realized that maybe granulation has nothing to do with magnetic fields.
No.
Okay.
I don't really heard you actually. So you're asking if the granulation is linked to magnetic field dynamo?
Yeah, basically I'm asking, can the Zeeman Doppler imaging help remove the effects of granulation? No, okay.
No.
Okay, so that was the easy question.
Because with the Zeeman Doppler imaging, you have only large scale field. It's very hard to have the small scale. So with the Zeeman splitting, you can have the magnetic field and so the spots or the flash, but you cannot have the resolution you need to see the granulation.
Got it. Okay. So my other question is, at the start of your talk, you introduced at least five different methods of basically determining whether you're seeing stellar activity, whether stellar activity is affecting the radial velocity. And then you focused on the spectral polarimetry. And I'm wondering whether you could compare the different methods. Like, have people tried, like, what are the advantages of this method of doing the Zeeman Doppler imaging over the other methods? Or could you try multiple methods and compare them?
Yes, if you want just to detect exoplanets, maybe the Gaussian process is more efficient and more is faster. But if you want to characterize the activity, the Zeeman Doppler imaging, particularly if you are in the infrared domain, will be very efficient because you will be able to see the magnetic field in the spots, and you can very easily take into account this effect because you directly work onto the profile instead of just the radial velocity curve. So it depends what you want. If you want to characterize the activity, it's useful to combine Gaussian process and demand Doppler imaging. Even if with Gaussian process you can have some characteristic of the activity. For example, it's a very efficient way to measure the lifetime of spots because you can add this parameter as a parameter in your quasi-periodic function that represents the jitter.
Okay, that's it from me. Questions from somewhere else?
Are there any from the room? Just yell them out if you have them.
No questions from Catherine?
Oh, something's coming up. Let's see.
No,
no,
I'm
she's
just
commenting.
audio.
So, can you hear me?
Yeah.
Okay. Elodie, so has this been used to find any exoplanets around M dwarfs? It would be difficult, but what?
So far with demand Doppler imaging, no, it's not successful, but we just target stars we really know to be sure we have the precision with TEPS to get the map and the magnetic field simultaneously. And we didn't discover any planet with this. And the precision of the filtering is not sufficient enough to discover, for example, a very sun-like, Earth-like planet. It's sufficient to have like 5 or 6 mass, Earth mass planets.
Mm-hmm.
How many stars did you target?
10.
10,
So,
okay.
Would having photometry, like with that at all help maybe like narrow down the contribution from certain spots?
For the to confirm or to confirm the map, for example, we get at the end of the imaging process. But we didn't have any measurements so far. But we could have this simultaneously. If you have photometry, radial velocity plus a magnetic field altogether, of course it's better. And for M dwarfs, honestly, the method will be maybe more useful in the infrared because in that case, you're less sensitive to the contrast, but you're more sensitive to the magnetic field. So the demand Doppler imaging will be more efficient to reconstruct the activity in that case.
But none of the upcoming instruments like Spiru or Common S, which has started working, they don't have a way of simultaneously doing photometric monitoring. No.
But we can ask to.
I know, but it's always harder to coordinate at 2 different instruments.
I think there is a project with Spiru to have a very small photometer in space.
Oh, okay.
Dedicated to Spiru observation, but it's not at the same time as Spiru, not for next year.
Okay.
Is there any limit as to kind of distance of the planet that you can detect using this method, like talking about hot Jupiters? Does the distance to the star make a difference?
Yeah, it depends on the star, the planet you want to detect. If it's a Jupiter, you can detect Jupiter till 2 or 3 AU, like in the first plot I showed you. Here. You see that all the hot Jupiter, so the yellow, orange, and red points, are hot Jupiter, and they're all between 1 AU and 0.01. So this is the sensitivity we have with radial velocity, because all this detection here, which are farther than even our Jupiter, are detected by direct imaging. So if you want to see very far, you need to have direct imaging. You're more sensitive. And for Earth-like planets, this is very, very, very close. I mean, Mercury or even closer with the sensitivity.
Are there any other questions from the room? Oh. That was the same one that you just made. Thank you very much for coming out here. I kept forgetting to move the camera. I was so interested in what you were presenting.
Sorry. Thanks for listening.
Yeah.
And thank you for agreeing to go first.
Yeah.
You're a guinea pig. Shall we throw it back to upstate New York?